So this is a simulation model built in Simio that has all the features that we need to represent our system and to obtain the cycle time corresponding to the different alternatives we might want to explore. So as you can see, we have these objects here, which are servers in Simio. You don't need to know that. These are just our stations, station 1, 2, 3, 4. And we also have 5, 6, and 7 in case you want to study the scenarios where we extended the number of stations. Okay. And we have amplifiers represented by this green triangle that go, these triangles go through all stations. If it's 4, after station 4, they will be shipped to these objects here, which is the one in charge of shipping the amplifiers out of the system. If we have 5 stations, they will come to this station and then will be shipped and so on. Okay. For every station, we have KPIs corresponding to the total busy time, stop time, block time, and failed. Okay. In our model, we don't have failures, so this is going to be always 0. Okay, this is in case you wanted to introduce some variability or in terms of breakdowns. Okay, you can, if you are familiar with Simio, you can tweak the model and introduce that. And we have this TIS, which stands for time and station. That gives you an idea of how much time, how long amplifiers have to wait till the moment they get into the station until they are released to the next station. Okay, and we have the cycle time, of course, for the whole system and the hourly production. Okay, and what you can change for you to analyze different configurations, for that you have these properties here. So first you have the number of stations, and you have the warm-up, which is not properly, it's not a configuration element of the information. It's just how much time you'll let the simulation model run until you start computing statistics. So notice that at the very beginning you don't have any amplifiers. So if you take that time to compute the cycle time, the value would be biased. So you let the model run for, let's say, in this case, that's 10 hours. This is time enough for you to have enough amplifiers in the system, and then you let them all run for 100 days, and then you get results. You can change this. You can put here a larger value, and in case you want to be really sure that you don't have any biased number, but this is enough because this simulation run is very long. 100 days is long enough. Okay, so you had the number of stations, which is 4 currently, and you have for every station the number of positions you have in case you want to duplicate the capacity of a station. At the very beginning we only have 1 position for a station. Okay, and we have the buffer capacity at the beginning, the entry station, the input buffer capacity for every station. Okay, so it's 0 for all these 3 stations, and we don't have any for station 1 because we assume that anytime station 1 has produced an amplifier or has assembled an amplifier, it has the necessary raw materials to start all over again with the next amplifier. If we change this 4 to 5, what we see is that we have these 2 values for station 5 and the same if we type 6 or 7. Okay, so depending on the number of stations we're using, we have to configure the corresponding values. So let's switch back to 4, okay? And that is for you to change the number of stations, or number of positions, and the capacity of the buffers. And if you wanted to change the capacity to 10, you have to just type 10, 10, and 10, okay? And if you want to change how tasks are assigned to stations, you have to go to this data tab. Okay, you come here and you have this table. Okay, in this table what you have is the list of tasks and the station you're assigning every task to. Okay, in this case, this is the solution we obtained from the optimization model. So Station 1 is where we performed tasks 1, 2, 3, and 5, and so on. And for every station, we have the mean and the variability, okay, which is the values we had in the previous presentation, and we have the probability of reprocessing. If we change values here, what we have is that taken into account when deciding whether to reprocess a part or not. So sorry, we need to get back to data. So you can change things here. Okay, you can just click here and change values using the drop down option we have here. You can just type in your value instead of having 3. You can type whatever. Well, you don't have to change the mean, but you want to change the variability and reduce it by half. Okay, you would be typing the 10m instead of 20. Okay, and the same goes for the reprocessing values. You can also copy this table into Excel, do the changes there, and then copy paste here. You can do that, or you can change every value one at a time, whatever you prefer. And that is where you have to change the variability and the preprocessing probabilities. Okay, and with those two columns and the buffer capacities and the number of positions, you have everything you wanted to do to introduce changes. And then once you have introduced those changes, you can, let's type here 0, 0, because at the very beginning we don't have any capacity. You can run the model. Okay, you can click on either run and see how the different amplifiers move. Notice that you only have amplifiers in these 4 first stations because we set the number of stations to 4. Remember that if we had typed 5, amplifiers would get to this point. But remember that if we type 5, we need to change this for you to use actually station 5. So you need to get the values you obtained from the optimization model, copy them into this table, and then run the model using 5 stations, and so on. And the same, if you decide to change the number of positions, you need to get the values from the optimization model. Okay, so you can also fast forward. Okay, you see this bar here advancing, and you'll get a result. I have to say that this is not the rigorous, the orthodox method to obtain the KPI corresponding to this system, because we are only running one replicate. What we should do is to run several replications and then get a confidence interval for the mean corresponding to the cycle time. Okay, in this case, we're assuming this is okay, but you could go and run an experiment. You can create an experiment here. Okay, new experiment, and you can decide how to change the values of these parameters and run several replications, and you would be getting in the results, or even if you define here responses, you need to know a little bit more about Simio to do that, but you could get a better estimate of the cycle time than just what you get from a single run as we are doing here. But let's assume this is good enough, because what I want you to do is to understand how the simulation approach works in comparison with an optimization as an extension, a complementary analysis to what we obtained previously. So let's assume this is good enough. Okay, so notice that if we run this model taking into account this variability, these processing probabilities, okay, what we get is that we are having a cycle time which is not 20 but 20.77. So we have less capacity than expected because we don't have room to store parts, because we have to reprocess sometimes the amplifiers, and because we have some variability. And we can check if things are okay by means of changing the values to our theoretical world, which is the one we assume to have in the optimization model. So let's imagine, let's come here, I'm going to change the properties. I can type here infinite. I did something wrong. Oh, sorry, this is not. Buffer capacity, infinite. Okay. Why is this wrong? Infinity. Okay, this is right. Infinity and infinity. So we're going to assume that we can store as many parts as we want in between two stations. Okay, I'm going to put 0 as the variability for every task. So the duration will be always be 3, 6, 7, and so on. And I like to copy this. Okay. And I'm going to set the probability to 0. So there's not going to be any reprocessing at all. So if I run my model now, what I expect to have is a cycle time of 20, because the time to process all tasks in station 1 is 20, remember 17, and so on. So exactly we get that value, 20. We have a busy time of 100%, 85%, 95%, and 100%, which are the theoretical values we were expecting according to the optimization model. Okay, so I didn't do that, but when I run the model, taking into account the reprocessing probabilities and the variability and the inexistence of buffer storage capacity, so you can get more realistic values about the busy, staffed, and block time of every station. So what you can do now is, with this model, you can evaluate the different options you evaluated first with the optimization model and see how or to what extent you overestimated the capacity of the production line. And for that or those scenarios which are more promising, you can analyze the impact of introducing changes. This is reducing the variability by half, these values we had here, changing these reprocessing probabilities to 0.5% for every single task. And finally, you can change the buffer capacities to have a 10 here, which is pretty much very similar to having infinite capacity in between two stations. So I think this explains or allows you to understand what is the impact of variability, and that you have hints to use the simulation model and explore different configurations with more valid and realistic results than the one you obtained from optimization. But I want to highlight that optimization is very valuable, because in this case, instead of trying different configurations here, which could take us quite some time, we had an optimization model that allowed us to explore what are the most interesting alternatives, at least when we assume a deterministic approach, and then we come here and analyze those in more detail. So these two approaches are complementary. If you just stay in the optimization world, you wouldn't be taking into account these features. And if you started right away with the simulation approach, you would have to work far more to obtain the optimal assignment of tasks to stations. So they were combined very well, and you can take advantage of the best of each world and get the best analysis for your system. So again, I think this has been useful, and I hope you can do a good analysis with these hints. Goodbye.